Okay, I'm going to admit this to you. I've been talking to a lot of NASA people recently. I just think I got on the press list, and could not be more gracious because I would not expect to be able to talk to high level scientists with such frequency. And last week or a couple weeks ago, I covered that we were shooting an asteroid. We're hitting it with a spacecraft. I've already lost that concept because I struggle to understand a lot of this space stuff. And this one, the thing that we're supposed to talk about today, I can't even conceptualize. So here's what I'm going to put forth. I'm going to try to explain what I think it is, what I think is happening, and you adjust and you tell me if I'm right or wrong, okay?
Sounds good.
All right. So on Sunday morning from Cape Canaveral, we will be shooting what I believe is kind of a satellite. It's kind of like a satellite, and it is a laser something communication system that will optimize our ability to see space by about 10 times. Now,
yeah, so
tell me where I've gone wrong. Tell me where I've gone right.
Right. So the launch will be for the STP-SAT-6 satellite. That satellite will be hosting a payload called LCRD. So you can think about the payload as the collection of electronics and optics and lasers that make up the LCRD demonstration, the Lunar Communications Relay demonstration. That satellite is going to go to geosynchronous orbit. That orbit is about 20,000, 22,000 kilometers above the surface of the Earth. The reason that you want to go there is because the satellite will essentially stay in the same place in the sky. So you'll be able to look up and see that spot in the sky, and that satellite will remain there, moving around just a little bit as the Earth rotates. And that's important because the relay part, the R part of the demonstration, is initially to be able to connect two ground sites together. One ground site is at Table Mountain facility in California. The other is in Hawaii. And those are high altitude sites targeting getting above the atmosphere. So the L in LCRD is lasers, correctly. We'll be using lasers to communicate instead of radio frequency, which is the most common communication mechanism we use now, particularly from space. And there are certainly many radio frequency applications at GEO. Satellite radio is clearly one of them, right? I mean, that's been around for quite some time. And so we're going to be looking to demonstrate communication from one site to another using lasers. Now, why do you want to use lasers?
You took the words right out of my mouth. I was going to say there's a couple things that bear explanation. One, is there another example of laser communication?
Sure. Well, we've done technology demonstrations with lasers in the past. In fact, quite a few years ago, we had a lunar laser communication demonstration, LLCD, that we used a laser to communicate from the moon. But that was a technology demonstration. This is actually an operational demonstration.
This is what I'm talking about. I'm talking about function. Does it have?
Yeah.
Is there a modern function with it yet?
Not right now. So this is really our first attempt to get to optical operational relay capability. And we're really looking to do the same thing we do terrestrially, right? Terrestrially, almost all of the data that is transferred in backhaul from site to site is already done with lasers. It's done, those lasers are bound up in fiber optic cables. And so we're not using cables. These are direct free space laser from point to point, from space to ground. And we want to do exactly the same thing. You want a fatter pipe to get your data. You want more data. You want it faster. You don't want to wait when your next episode is coming from your streaming service, when you're binging. You want to keep getting that data, and we want to get as much as fast as possible, and that's why we're moving the lasers.
So I'm going to try to put it into softer terms. So we are shooting up a rocket, which is carrying a payload of a bunch of technology. Some of it's lasers, Some of it's like stuff that make the lasers work, yada, yada. That will be shot up, and it will be the midpoint of technology between California and Hawaii.
Yeah, for testing, yes.
Cool. What is the future application of this? What is the thought process going into this? How could this be beneficial?
So we try to leverage all of the lessons we learn ever forward, right? Because we're always trying to assemble an ever-growing puzzle from little pieces. And so the R in the LCRD, again, I mentioned, is the relay part. We have a lot of experience operating relays around Earth. In fact, many decades of operating relays around Earth from the TDRS system, tracking and data relay satellite system. That's RF based. And that gives any location on Earth real-time access to get its data from one location to another. If you're in a challenging location like McMurdo Station in Antarctica, you sometimes need help getting your data from your source location to the target location where someone wants to analyze it, right? And so that's where relays come in handy. Relays are also useful for space users. So having that real-time 24/7 access capability is important to make sure that you can deliver your data in a priority fashion. Now, what's the lesson learned for the future? If we want to think about sustainable presence, crewed or robotic, throughout the solar system, the moon right now with the Artemis program is our target. So once we think about sustainability at the moon, where you have crew living and working on the surface, you have many assets in orbit around the moon, as well as in cislunar space in between that are supporting, right? Because you may have to be have a logistics chain that is delivering things from the Earth to the moon, and likewise from the moon to Earth. You need to have a complete communication and navigation architecture to enable that. This LCRD demonstration is a step in that puzzle piece assembly, because we'll use that Artemis program, the lessons learned about how to do sustainable capability, leveraging those lasers to give us those fat pipes for the data back to Earth, to think about what we would need to do to enable crew at Mars, right? To be able to have sustainable presence at Mars. And really any place in the solar system where we want to have a large volume of data to come back and analyze, because you don't make discoveries without data. And the more data you have, the more discoveries you can make.
I have so many questions, but I'm going to go with a quick one. I'm going to ask a quick one. And I'm going to ask you to explain lasers, because you said that there's lasers in the wires. You say that these lasers are going to be in the sky. And I know that I think the public probably has a hard time conceptualizing lasers. So I guess the first question is, will the laser have a beam? Will there be any light? Will it be visible?
So there will be light. It is a laser light, but it's not visible. It's in what we would call the near infrared.
So it's like you need a UV light or something.
Right, but lower.
Okay.
So the humans see in a wavelength sense, humans see something like from 400 nanometers, where one nanometer is a decimal point and 8 zeros followed by a 1, so very small. From about 400 nanometers, which is UV, down to about 700 nanometers, which is the red. And so these lasers are bigger waves than that, so below red, at about 1550 nanometers. So if you think about a micrometer, so a decimal point and 5 zeros in a 1, human hair is about 30 micrometers. And the laser wavelength for these lasers will be about 1.5 nanometers. So quite a bit smaller.
So second question about lasers. Is there any like ramifications of having a free flowing laser?
Sure. It's electromagnetic energy, right? And if you think forward about those puzzle pieces for sustainability with crew at the moon, for example, whenever you have crew tending a vehicle or tending a location where they're living and working, you absolutely must consider every aspect that impacts their safety. That is specifically why we chose the wavelength of these lasers, this 1550 nanometer frequency, is because it's eye safe. So you would not receive damage from having one of these beams intersect your eyes. They're not dangerous for you to walk in between them, so they're low enough energy that they wouldn't hurt you, and you could avert damage to your eye specifically because of the wavelength choice.
And nothing with like planes or anything flying through it?
So that's a great question. We actually, there should be no issue with it because, again, of the choice of the frequency that we are operating these lasers at. However, we do coordinate with all the relevant federal agencies, FAA, and something called the Laser Clearinghouse, to make sure that during our experiments, we will not be inadvertently illuminating any aircraft or, in fact, any spacecraft that might be between our source and sink, our transmit and receive for these laser beams. So
And
safety is paramount.
yeah, no, I was thinking about that because I just don't know. I don't know enough about lasers. I don't think the general public knows enough about lasers. Beyond that, you're mentioning moon stuff, that this could be useful for moon exploration, something like that. Is that something that NASA is working back towards? Because a criticism I've had about just life in general, and is that we haven't had anyone on the moon in my lifetime. And I think that it would be a great morale booster just for humanity to have a person on the moon. It sounds like you're talking about moon stuff. Is that something you see, or is that something that's thought about often?
Absolutely. It's a essential piece in our Artemis program, right? Remember that Artemis 1 will soon be sending the first craft around the moon again in preparation for the Artemis 2 mission, which will be the first sending of humans back around the moon, right? That'll be testing that we can get humans out and back safely. And that is, again, precursor to Artemis 3, which will be actually the return of humans to the surface of the moon. And in fact, we have a laser payload on Artemis 2 that will be our test of optical communication technology from a crewed vehicle, from the Orion vehicle. And so it absolutely is playing a part in the future puzzle assembly of what sustainability will look like at the moon as part of the Artemis program. And I'm very excited to be thinking about and working on these things to enable this capability for the future.
And beyond that, we're looking towards the year 2100, as I prefaced. Where do you see the future of? Actually, we'll stick with just the lasers for now. What potential growth could you see of this technology for the people of the year 2100? Do you have what role do you think lasers will play?
I think so I think there's two aspects to that. One is, it's, as everyone already knows, it's very difficult to predict the future, right? We never really know where things will go. I mean, who knew that a little known investment from the old ARPA program would turn into the internet, right? And what we have today with business commerce and the ability to stream music and video and have all the stuff on demand. I think clearly going forward, even in the relatively short term, lasers with respect to space communication are going to serve that purpose. And in fact, it's already moving in that direction now. If you think about all of these satellite constellations that are commercially being built up, you think about like Starlink and the other commercial capabilities, they're already using lasers to do space-to-space links. So that is lasers to communicate data from one spacecraft to another with no atmosphere in between. Those links are much, much easier to use and have hardware that is commercially available. The challenge is the space to ground link because of the atmosphere. And again, that goes back to what we're planning on learning for the operational impact of that capability for us with the LCRD project. And so that future clearly will be lifting the terrestrial network up into space, because if you can transfer the data out in space, you can get it to your location faster. That extends directly to the moon. All the activity that would be going at the moon, you would collect that data and send it back through a fatter pipe to the Earth to eventually be delivered to the ground. That exact same scenario of lifting that network up and having networks of networks, just like the internet on Earth, to be able to have a LunaNet, a network at the moon that has relays that relay optically data to Earth, a MarsNet that would support crude activity at Mars. That could relay data to the moon or to Earth. It depends on what is the best way to get your data from point A to point B.
And I've been told we have time for one last question. I just want to say thank you for talking to me. I appreciate this. This has been very informative and interesting. Last question. I've been noticing a lot of with NASA, the types of missions we're going on. Like last week, the DART mission with the asteroid, and this we're doing lasers. And I believe next week I'm talking to someone about X-rays. Is something going on? What is going on? I'm seeing a lot of productivity. Is this all in collaboration for Artemis 3 and getting to Mars and stuff? Have you guys like picked up the slack? What is going on? I'm just seeing a lot out of you guys.
We're busy beavers.
Yeah.
we do a lot of things, right? So you mentioned X-rays. One of the things that we do is we learn by leveraging the entire electromagnetic spectrum, from the very, very low radio to explore other galaxies, all the way up to X-rays to explore other galaxies, and everywhere in between. So that's one of our specialties, is we look at how to exploit the electromagnetic spectrum over its entire range to collect data that enables us to make discoveries, because technology drives exploration.
Last thing, do you have anything that you'd like to say to the people of the year 2100?
I hope the lasers are still working.
All right. Well, this has been great. Thank you so much for your time. This is Dr. Jason Mitchell. What is your formal title with NASA, so I don't get it wrong?
Formal title is I'm the director for the Advanced Communications and Navigation Technologies Division in the Space Communication and Navigation Program at NASA.
And you see why I had you say that, because that's a paragraph.
I have trouble too.
No, thank you so much. I appreciate it.
Thank you for your interest.